Good afternoon. Thanks for showing up. Some familiar faces here. My name is Brian Montgomery. I'm with Western Michigan University, and today's presentation is going to be on global flow diagnostics and experimental aerodynamics, an image-based approach, which is summarized by moving away from local measurements, single points of data, into global measurements. My background is Department of Defense, specifically encrypting GPS geolocation on imagery-based platforms, full motion video, and I did extensive amount of time at the Central Intelligence Agency. So this is basically a presentation about local measurements versus global measurements. Local is limited by spatial resolution, typically one data point per sensor, like one pressure tap. It's very intrusive in the case of a lot of the pressure taps need to be installed in geometries that are very thin in nature and not physically possible to install the pressure tap. It's very expensive and very time consuming. The pressure taps need to be calibrated, where conversely, global measurements provide a high spatial resolution and typically one data point per pixel, non-contact because it's image-based, and it's relatively easy application. The image processing's a little bit more time-consuming, but not nearly as labor-intensive as the test methodology. So we have local pressure taps, which is one data point per sensor, and you can see there on the airfoil the maybe 25 or 30 pressure taps. The same airfoil with pressure-sensitive paint derives one data point per pixel, and then you can see you get, instead of 30 pressure taps, you have approximately 1 million data points. So integrated flow diagnostics toolbox. So with the exception of temperature-sensitive paint and pressure-sensitive paint, everything on here has been developed and derived at Western Michigan University. So for example, we're able to derive pressure from skin friction using global luminescent oil film, which is an oil thinning application. Temperature-sensitive paint, we're able to derive skin friction from TSP and skin friction from PSP. And what we currently have been working on and just patented 2 weeks ago, or we've applied for the patent, is a 3D photogrammetry. So velocity, so optical flow, velocimetry, which is typically, a lot of people associate that with PIV. We've developed what we call optical flow method. And so that's used for the extraction of 2D velocity fields, measures the flow displacement by solving the optical flow equation. And instead of having the interrogation windows, however many of those may be, with the average of those interrogation windows for that vector average, we actually have a high spatial resolution, which is one vector per pixel. So it's ideal for images with continuous patterns or large scales, such as satellite imagery, planetary, atmospheric sciences, and we're going to get into all of that later on. Now, let me just preface this by saying I have a lot of slides, it's a lot of visuals. I'm not going to take questions because it's going to use my whole time slot, but we have a booth right over there, Western Michigan University. So if you want to come over, we're here the rest of the afternoon to take questions. Optical flow, what I call optical flow method, is applied to, in this example, a space orbiter 3D printed object, which we have over there in our 3D printed wind tunnel. And the experimental setup is a planar laser, a side optical fisheye lens camera, seeded flow, which in this case is glycerin, vegetable glycerin smoke, a rear camera, and then you can see some of the OFV images. And then through the image processing, which is similar to PIV, but it's more accurate because of the optical flow method, we're able to derive the velocity magnitude and the vorticity around the Space Shuttle orbiter. So thinking outside the box, we we realized that optical flow method has multiple discipline applications. And in this case, we have a PhD student that's currently working on wind flow around residential buildings at different angles of attack, different velocities. And why is that important? Well, it's important because as many people like to understand wind dynamics, whether it be tornadoes or hurricanes, they do not. So we have positive pressures, we have negative pressures, and so what we want to do with this study is to develop a load protocol so we can truly understand at the molecular level wind dynamics associated with residential structures. Once we're able to do that, we can step back and start to look at building codes and various connections and load path transfer to make these things safer and more resilient, susceptible to hurricanes and wind. But here you can see the side view of just the standard test, a slowed down view, the velocity, the average velocity and the vorticity calculated. And then a top view with the same calculations. And then with satellite imagery, so we're able to look at of course we can't penetrate the cloud canopy, but what we can do is image the top of that cloud canopy and then calculate velocity vectors and pressures down to ground level. And we looked at Typhoon Ray in the Philippines and with a series of IR imageries that were downloaded by NOAA data. And then we're able to run through the image processing program, and we were able to calculate the average velocity field. And you can see that the hurricane model versus the measured data, it's almost an identical curve. Now, more locally to Michigan, as climate, we never used to have tornadoes. Now it seems like we have 2 or 3 or 4 tornadoes every year. And we had one that hit real close to home. As a matter of fact, so close, it's only about a quarter of a mile from our research lab at the airport. But May the 6th last year, we had a tornado. I believe it was an F2. Velocities up to 135 miles per hour. It completely destroyed a FedEx building, as you can see from the overhead images. And what we wanted to do was to employ optical flow method at a more local level, because this was all over the news. So what we did was we looked at the raw images, again captured by NOAA, and we were able to calculate the instantaneous results, or the total pressure and the wind speed in meters per second. And here's the real summary. Of course, we wrote a paper of this that was funded by Repowering Schools, which is a STEM organization. We were able to calculate the wind speed, and again, this is based off the canopy of the tornado, and then a series of calculations that go all the way down to ground level. But we're able to look at the wind speed, which is very interesting because it's less than 50, 60 miles per hour. But then look at the total pressure, because where that total pressure accumulation is where the building was destroyed. So it doesn't tell us the structural integrity of the building, but it does tell civil engineers, structural engineers, why that building failed and why other surrounding buildings did not, based on optical flow method from weather satellites. So the next step, we just filed for the provisional patent a couple weeks ago. It's to develop a 3D photogrammetry optical flow velocimetry. So that eliminates particle triangulation and the tomographic reconstruction. Instead, we use that perspective projection transformation, point correspondence, and link optical flow velocities to 3D motion in an object. And we'll get into the setup there for that. So it's quite easy, but you can see that the nozzle, the pump, this is underwater, the camera setup, the calibration step, which is required for each collection method. Once you do the calibration step, then you remove that, and then you do your actual physical test. And so with one camera, you do it 4 times, 4 collection methods 4 times, and you can see the underwater nozzle, single camera setup, the camera calibration setup, and then the nozzle in image 1, 2, 3, and 4 on the raw images. And so here's the steady state velocity fields for each image, and then the calculated 3D velocity fields. And I want to point out here that this is a very large volume measurement because it goes from 0 to 2.5 inches, and it's 1 square inch on the Z. So comparative to other things that are commercially available that cost multiple hundreds of thousands of dollars, this volume measurement is over double or triple what's currently available. And again, all this was developed at Western Michigan University. Skin friction from GLOF, this is really near and dear to my heart. It's one of my favorites. Basically, it's ideal for complex separated flows. It extracts high resolution skin friction topological data. It's based on a thin oil film equation, which is basically, it's a thin oil film that you can see here in the setup, which is applied with a foam brush. And the viscosities vary anywhere from 100 centistokes to up to 1,000 centistokes because we're trying to defy gravity here when we actually test these models. But we have a thin oil that's that's doped with a dye, a luminescent dye, and it's excited with a UV lamp. It's placed on a mylar layer. In the case of the residential building, we had mylar on top of the 3D printed buildings. And it's a silicon-based with the UV tracer. And again, typically we use around 100 to 200 centistokes. Developed at WMU. It's an inverse problem based on the Navier-Stokes equations. It's a very, very high resolution skin friction pressure distribution, and it's ideal for low speed incompressible flows. So once again, we're able to apply this oil film, run through a 15-minute test, do multiple hours of image processing, but at least we don't have to worry about calibration of pressure taps or even the placement of the pressure taps, because in the case of some of these models that you'll see that we performed, there was no way to install a pressure tap. So here's the GLOF application on the space orbiter that we have over there in our 3D printed wind tunnel. Again, it's a top camera excited by UV lights, side camera pointed to the space orbiter, and then the direction of flow. You can see some of the examples of the GLOF images. Here's a top view, a GIF image. Again, this is oil quenching, so this is a increase luminosity is proportional to decrease in skin friction and pressure. And then we're able to extract skin friction vectors and skin friction lines. So we're able to look at the reattachment and the detachment of the flow. And again, skin friction magnitude and surface pressure calculations. Here's the same application on a blended wing body. Again, this was 3/4 of an inch, maybe. So there was no way to install pressure taps in this. GLOF application on a driver vehicle, specifically for Ford Motor Company. So it has multiple applications for multiple industries. And then again, for our residential building, you see the horseshoe crab effect here in the GIF image. That's the ground effect, but it clearly shows the horseshoe crabbing, the detachment and the reattachment, and then the negative surface pressures on the backside, which causes the whole roof to blow off. So we do that at different angles of attack and different velocities. My goal here, full disclosure, is to create a new ASTM test methodology that will change building codes in the United States, specifically for wind-prone areas like southern Florida, South Texas, Oklahoma. And NASA Faith Hill, a standard model, and we applied the GLOF there. Again, these have all been verified through validation using pressure taps in this case. And on a delta wing, again, here you can see the good separation and the attachment, and then the comparison with the pressure taps. So although not one-to-one, it's very accurate. And then underwater measurements, we're currently in the process of building a new fluids mechanics lab, but this older lab here in the upper left, you can see it's basically the same setup. You have the UV lamps, the test section, and the camera. The difference in the underwater is it's normal to what we test in the wind tunnel, and to help defy gravity. And you see the flow direction here. And again, it's the same test, it's the same image processing, similar Reynolds numbers, and you can see the difference between here. So currently have some undergraduate students that are looking at senior design topics using underwater GLOF application. So it'll be interesting to see what they come up with. Stepping back just a bit, with the GLOF application, especially with spinning things like rotating propellers, rotating blades, there's no way to measure the pressure associated with that using pressure taps because of the spaghetti nature of the hundreds of pressure taps that would need to be installed. So GLOF is a good solution to look at rotating geometries. So the underwater measurements, you can see the sample GLOF images on a delta wing, water versus air. Again, you can clearly see the separation and the reattachment for the skin friction magnitude in water and air. And again, the overlapping curves are amazing. There's a little difference because of the Reynolds number, but they're basically matched up perfectly. Surface temperature, TSP, something I know little less about, but again, we'll field all your questions over there at our booth at the end of this presentation. TSP, nothing new, but what is new is that we're able to extract skin friction from TSP. That is new. It's basically thermal quenching. It's a high resolution temperature distribution. It is, of course, it's non-intrusive. Skin friction was developed at Western Michigan University, and it's based on the inverse problem of the energy equation as shown here. Here's the setup. Computer power supply, illuminating light, luminescent emission, and of course you have the painted surface, and you also have to have a calibration. There's no thermal gradient. It has to be thermally calibrated. So ambient temperature doesn't work. So typically you have silver copper coated conductive layer, or sometimes nanotubes that provide that calibration thermal temperature. And here you can see that set up with the multi-layer heated coating. And it provides an instantaneous temperature distribution. And then what we're able to do at Western is extract steady state skin friction from that test. And then the CRM model, again, they use nanotubes for their temperature calibration. But what we did was NASA came to us, and because they don't have the capability to extract the skin friction, they came to us to employ that technology. So here's the results. So basically we were able to get, we were given the temperature distribution, we were given the national transition, but you can see here you have the turbulent wedges, and what we were able to do with those turbulent wedges were extract that skin friction magnitude, as well as look at the separation and the attachment of those vectors. PSP, pressure sensitive paint. So this is oxygen quenching. And again, it's high resolution, non-intrusive. At low speed, signal to noise ratio is very, very large. And again, at Western, we're able to extract skin friction from PSP. It's inverse problem based on Navier-Stokes. It's similar to pressure from skin friction, and again, it has a higher resolution pressure distribution. So again, non-intrusive, so once again, pressure taps aren't required. Here's kind of a schematic of how the test setup works. Illumination source, a photo detector, oxygen molecules because it's oxygen quenching, and in this case with an impinging jet, it actually, there's a temperature problem because the jet nozzle produces a cooling effect. And what we're able to do on the next slide, well, you'll be able to see here the temperature profile of the cooling effect here based on that setup, and the uncorrected pressure versus the corrected pressure. Again, David over there, he's the expert on TSP and PSP, but he'll be able to walk you through that that correction evolution. And a hollow cone cylinder. Again, I don't know much about this, but I do know that the surface pressure, PSP, and you have these boundary layers. So the fact that we're able to measure the surface pressure at these different boundary layers could have effects on a friend of mine at the University of Illinois, wind engineering. He's very interested in boundary layer studies at water-air interaction. And so this skin friction and surface pressure derivation we think has fundamental applications for wind engineering programs too. And then this is interesting. So the shock wave boundary layer interaction. You can see the region of interest there at the bottom, or the bottom of the test chamber, and then the normalized pressure, and then the separation bubble based on the PSP. And the conclusions, image-based flow diagnostics, I mean, it's just my opinion, but I've had a lot of interest from large industry partners. You know, we have to navigate away from pitot tubes and pressure taps, because those are singularities that don't give you a lot of data, and times are changing. Technology is evolving, and it's nice to see the students here before I got up here, because they have these open minds, they're willing to learn, they're willing to patent, they're willing to look at innovative technologies and apply them. And so I see that in our senior thesis designs as well. But it's non-contact, non-intrusive, extremely high resolution, millions and millions of data points, and it's relatively easy application, 15 minutes per test, tops. It's the image processing that's a little bit more complicated. And capable of extracting flow velocity, both 2D and 3D. It's applicable in air and underwater. And I might also add in a vacuum environment. Skin friction, able to extract surface pressure, surface temperature, and solid body deformation. So with that, that's my conclusion. I invite you all to navigate over to our booth to look at our K through 12 3D printed wind tunnel, and to talk about our optical flow method and how we can help each other navigate against hardwired technology and into more of a optical flow method. So thank you for coming, and thank you for your time.
Thank you.